Distinct patterns of within and between module connectivity during word reading are associated with different reading-related skills in children. Reading relies on several distinct cognitive functions, each of which require the processing of information within and the transfer of information between broadly distributed cortical systems. The system associated in single-word reading are distributed among several canonical large-scale networks. We can index this information transfer by analyzing the sensor-by-sensor synchronization of EEG signals. If we model this communication as a graph or a network, we can use modularity analysis to first identify independent systems associated with distinct reading-related cognitive functions, and second, characterize how connectivity within and between these systems support the development of reading-related skills in children.
So what are these modularity analyses? First, modularity is a metric from graph theory that quantifies how easily we can divide a network into distinct subnetworks or modules. Now, we can calculate modularity of a given partition of a network into modules, like we see here, by first looking at the connections that are greater than expected based on some specified null model, E in this term here, and then comparing the number of those connections that are within a module to the number of connections that are between modules. So a network with a high modularity statistic is going to have a higher proportion of within module compared to between module connections. And we can find the partition that happens to maximize this modularity statistic algorithmically. Now, it's important to note that we can modify the use of the null model in this term here so that rather than looking at the set of connections that are greater than expected from chance, we can look at the set of connections that are found during one condition of a task, but not during others. So here, we're particularly interested in looking at the set of connections that are observed when processing words, but not when processing word-like stimuli, so anything that lacks semantic content. So what changes in modularity do we expect to see as children's reading skills develop? Well, any cognitive function requires integration between systems, and that's going to directly reduce the modularity of the entire system. Interestingly, however, as a task becomes more automatized, we see a weaker decrease in modularity. So this effect here, where we see a decrease in modularity with cognitive effort, becomes less pronounced. This is explained by the neural efficiency hypothesis, which says that cortical systems will tend to limit any unnecessary communication as a process becomes more automatized. So, given that the automatized processing of single words is so important for reading, we suspect that these word-specific networks we're analyzing, again, where connections exist for words but not word-like stimuli, we expect them to show an increasingly independent configuration as children's reading skills develop. This leads us to three predictions. First, we expect these word-specific networks to have higher modularity. Second, higher within-module connectivity. And third, lower between-module connectivity as children's reading skills develop.
So for our methods of our study, our sample included 72 children in grades 3 to 5. The children were given 4 standardized tests that measured vocabulary, sound processing, fluency, and reading comprehension, all fundamental skills important for reading development. A 32-channel EEG was recorded while participants viewed 60 word and word-like stimuli, in which the word-like stimuli lack semantic content. Standardized pre-processing steps were applied, and trials were filtered at 4 to 7 Hz, the theta frequency. A cross-trial phase-like index was calculated, leaving us off with sensor-by-sensor adjacency matrix for each time point, for each condition, for each participant.
From these adjacency matrices, we then calculated global modularity over time relative to the baseline period for each of our 4 conditions. From these modularity over time waveforms, we identified peaks, and we selected time windows surrounding these peaks. We then created networks where the connectivity was seen for words within these time windows, but not word-like stimuli, and we analyzed whether the modularity of those networks was significantly greater than we might expect based on chance by analyzing its rank within a null distribution that we created using permutation testing. From any significant effects, we analyzed the modules that were driving those effects, and we correlated the connectivity within and between these modules with reading-related skills. Here you can see how modularity tended to change over time in each of our 4 conditions relative to the baseline period. The first thing you'll notice is that there was a distinct decrease in modularity regardless of condition during task processing. You'll also notice that this was particularly prominent at 2 distinct time windows, one from around 200 to 400 milliseconds and another from around 700 to 900 milliseconds. We found that the word-specific network created in this time window, where connectivity is seen for words but not letter strings, was significantly more modular than we might expect based on chance. It was in the 98th percentile of our null distribution.
Next, we wanted to know, what modules were driving this effect Jonah was just talking about. And when I say modules, I mean sets of nodes whose mutual connections were stronger for words compared to letters at this 200 to 400 millisecond time window. We found that modules tended to overlap with sensors that were located at frontal, central, and posterior regions, as you can see here on the slide.
Our first prediction is that we would see higher modularity in word-specific networks as reading skills increased. Indeed, we found that global modularity of these word-specific networks was positively correlated with vocabulary. As vocabulary increased, word-specific networks became more modular. Our second prediction was that we would see higher within-module connectivity for these word-specific networks alongside reading skills. In fact, within central modules, we found that increased connectivity was positively correlated with sound processing skills, and that within frontal modules, connectivity was associated with fluency skills.
In relation to our third prediction, we believe that as children's reading-related skills develop, we'd see lower between-module connectivity in our word-specific network. In fact, if you take a look to the left-hand side of the screen, we found that children with higher vocabulary ability show less connectivity between frontal and central modules. However, if you take a look to the right-hand side of the screen, we see the reverse pattern, in that children with higher sound processing ability show more connectivity between central and posterior modules.
So, do our word-specific networks become increasingly independent as reading skills develop? For the most part, they do. We did in fact observe higher modularity, higher within-module connectivity, and lower connectivity between frontal and central modules. However, we also observed higher connectivity between central and posterior modules. Now, it could be that we simply lacked a sufficiently wide age range and that certain changes of between module connectivity that we will observe as a process becomes automatized have simply yet to occur. It could also be, however, that reading is a qualitatively different process than those for which this automaticity-induced change has been observed before. Now, this might be plausible given the relatively recent advent of reading in evolutionary terms. So if you have any questions, please feel free to reach out.